Good afternoon to those of you on the West Coast, and good evening for those on the East. Thank you very much for joining us today. This is the 2026 Virtual Orchard Meetup Series. And this has been a few years going now and continues to evolve and expand. And so it's wonderful that everybody's able to join. So over the next few weeks, we're going to be talking about managing climate stress in fruit production, sun injury, ripening disorders, and post-harvest quality in North American orchards. And I want to just take a moment and just acknowledge that this series is actually sponsored this year by a national team of researchers and extension specialists working on a multi-year USDA SCRI project focused on evaluating management practices to reduce crop losses from severe cold and heat events. This large collaborative effort is known as SPARC, and that stands for Strengthening Pear and Apple Resilience to Climate. So it's my pleasure to be joining you today. My name is Kristy Grigg-McGuffin. I am the Apple IPM specialist with the Ministry of Agriculture, Food and Agribusiness, and that's in Ontario, Canada. And I'm actually a member of this organizing committee for the series, and I'm joined by a number of my wonderful North American colleagues who are also part of this committee. And I just want to take a moment and acknowledge them. So Lindsay King is with British Columbia Ministry of Agriculture. Emily Lavely is with Michigan State University. Mario Miranda Sazo with Cornell Cooperative Extension. Daniel Weber with Penn State University. And Bernadita Salado and Sonia Hall are with Washington State University. So we really appreciate everybody joining. I do just want to take a moment. I think that the poll is still up, so everybody can continue to enter in those questions if you'd like to participate. But I do just want to take a moment for some housekeeping, and then we'll get going. So just a reminder to everybody, if you could please keep yourself muted while the presentations are going on. Because our day today is pretty action packed, I'll switch to the next slide so we can see kind of what we've got lined up for today. We're going to be talking specifically about the physiological impacts, forecasting, and monitoring tools related to heat stress. But because we have a number of speakers that are joining us, we're going to hold the question and answers to the end and kind of cover that as a whole. So at that point in time, you're welcome to raise your hand and unmute yourself. Or at any time during any of the presentations, please enter your questions, comments, whatever you may have in the Q&A or in the chat box. And we're monitoring that. And so we'll bring that forward during the Q&A time. So I think with that said, we're going to get started. So I'll introduce our speakers kind of as we go. And so to start things off today, I'd like to welcome Emily Lavely. She's the tree fruit educator with Michigan State University Extension. So Emily, I'll stop sharing and then you can jump in there.
Okay. Thank you, Kristy. Okay, sharing the right screen. It looks like on my end. Okay, thank you. Yeah, welcome everyone to our webinar. So I'm going to set the stage to just kind of talk about some of the symptoms that we see related to heat stress. A lot of my pictures are from Michigan, so that's what you'll see today, but I know this is something that is experienced all across North America. And so I also put up the SPARC logo, like Kristy mentioned. This is something that has really drawn me to trying to better understand sunburn and heat stress, this project. And I'm the Michigan Extension lead for the project, so I'm learning a lot and trying to understand what's impacting our growers here in Michigan. So sunburn can be any type of discoloration or physical damage or death to the fruit that's caused by sun and solar radiation. So we see this damage when we have elevated fruit surface temperatures. And you can see here, this is just a picture of younger apples. So these were about golf ball size on the tree. And you can already see that sunburn appearing just with that dark tissue. So we can see symptoms either develop in the field or even show up in storage. And these symptoms are caused by excessive exposure to sunlight and experiencing high temperatures for a long time. So we can see damage on the skin. And I'll show some pictures of that going forward. But we can also see damage in the flesh as well, under the skin, or I think later on in our series, we'll get into more of those disorders, but even seeing damage into the fruit flesh itself. So one of the things I wanted to mention too, and I wanted to talk about this because I know other regions experience this as well, but we had a very dry season last year in Michigan. And so just recognizing that sometimes when conditions are dry, we have low soil moisture or that the humidity in the air is low, you might see more issues related to sunburn and heat stress. I'm going to talk about the three different kinds of sunburn that we see. So the first one that I'll talk about is the sunburn necrosis. So it's this really dark necrotic spot on the tissue on the outside of the fruit that can turn dark brown or black. And we see this when the surface temperatures are really hot, so 125 degrees Fahrenheit or 52 degrees Celsius. And it can happen quickly in as little as 10 minutes under the right conditions. And we see some of these symptoms even when the fruit are small. So again, kind of that golf ball size, that's where fruits start to become more susceptible to sunburn. And we can see damage on the skin. And just what happens over time is a collapse and breakdown of that tissue. And this type of damage can also be seen really quickly within 1 to 4 days after seeing that exposure to those high temperatures. And then another problem that can happen with this type of sunburn is that once that damage occurs, and you can see here in the picture, there's some cracking of that tissue, there are secondary pathogens that can come in and start to degrade the fruit, and then that can become a source of disease for other apples in the orchard. So this can be a real problem, particularly earlier on in the season. Another type of sunburn that we see is sunburn browning, and this is damage that happens on the exposed side of the fruit. Sometimes for me, it's hard to see almost because for some varieties where the skin's already a little bit orange, you might see, like you see here in these pictures, you just see more of this orange tint, so it can look a little yellow, brown, or bronze, or even dark tan. This is something I've seen on Evercrisp here in Michigan, which does have kind of an orange tint on the skin. So it's something to just look for as you're looking around orchard blocks. So this browning is caused by high solar radiation, and it leads to really high fruit surface temperature. And different varieties also will experience sunburn at different temperatures. So for example, Cameo and Honeycrisp, they can experience this type of sunburn at 115 degrees Fahrenheit or 46 degrees Celsius. And Pink Lady can have sunburn at 120 degrees Fahrenheit or 49 degrees Celsius. So you do see some differences in varieties, even depending on the parentage of that variety. You might see differences in susceptibility to this kind of sunburn. So this is the most common type of sunburn that we see. And I've seen this also in here in Michigan where we've had more cloudy days. And then all of a sudden in the fall, the fruit's really close to harvest and clear skies. It's beautiful, beautiful fall weather. But then all of a sudden, 2 weeks of that, and you start to see sunburn on the trees. So this can be one that pops up when you don't expect it or before harvest. All right, the other type of sunburn is photooxidative sunburn. So this is sunburn that happens when apples were in shade and then they are exposed to full sun. So you can see, like in the picture, there's a bleaching that happens where the skin gets really white, and then over time it will turn more of a dark tan or brown color as those cells start to break down. So this is something caused just by that exposure to solar radiation, and it can happen at cooler temperatures. So sometimes this can be a surprise. Things that can impact this type of sunburn, even things that we do in the orchard to try to improve fruit color might be things like hand thinning, color picking, or selective picking. If you've got a branch that's heavy with fruit and it starts to move down from the weight and exposes fruit, you can see this kind of sunburn, or summer pruning or leaf removal. So trees try to handle the stress. Unlike us, that where we can move into a building and try to cool down, trees can't move, so they have to figure out ways to help keep their canopy cool and keep protecting the fruit. And one of the primary ways that they do this is by releasing water through evaporation through their stomates in the leaves mostly, and then in the fruit. And just like when you get out of the pool and you feel that water start to evaporate, you get a little chilly. That's what the trees are trying to do to just keep the canopy a little bit cooler. I mentioned this earlier, so the ability for trees to do that when it's dry really declines. So because the tree might be water stressed, it will close those stomates to keep the water from being lost, but that means it can't regulate canopy temperature very well anymore. So that's why you might see more sunburn in those types of situations where conditions are dry. And we'll talk about this more in the next webinar, but how do we deal with these types of sunburns? There are really two approaches. One is being able to change the environment somehow, whether that's evaporative cooling or covers, or changing, being able to protect and cover the fruit surface, so putting on a type of sunscreen. And then I wanted to just mention a couple other things too that I've been seeing and I know other people are talking about. But really the way that we're growing trees makes our orchards more prone to this type of damage. And so changes in tree architecture, going to really narrow canopies, high density trees, and training branches so they're along wires. I think these are challenges when we talk about things like automation, where we want a really pristine orchard where the branches are trained. In some ways, we're creating these environments that also makes trees more susceptible to sunburn, and especially as the weather patterns. And I know our other speakers will talk about that, but as we see high intense periods of heat, those are things that we're going to have to really deal with and try to find solutions for as an industry. So, and you probably know trees that are exposed to sun or in the top part of the canopy. So where they are within the tree canopy, that can lead to different risks for sunburn, versus tree apples that are in the tree and being more shaded. All right, a couple other things that I wanted to mention related to sunburn and heat stress. So the fruit development stage can really impact the level of risk, and these factors related to heat really have an impact on fruit maturity. And you can see this picture of browning. So that was something that was common here in Michigan one season, and we think that it was related to temperature before harvest. And heat can really push maturity and advance it quickly. So the other thing that is something that we've been exploring a little bit here in Michigan, but just thinking about, and I'll show a graph here in a minute, thinking about when an apple experiences 125 degrees on the fruit surface or a 95-degree day during the daytime, but then at nighttime it gets really cool. So that the temperature that the apple's seeing is 40 to 50 degrees different in a single day, thinking about how that could impact the fruit quality and internal browning and sunburn development. So this picture here is an apple that has wires coming out. So those are actually thermocouples that measure temperature. And we put them in different parts of the apple to just try to understand what the different parts of the apple were experiencing as far as temperature. So here's an example of some temperatures here in West Michigan. So that's where I'm based. And I just wanted to show you what our season can look like. This was from 2025 last year. So we've got temperature in Fahrenheit and then going through the season by date in the fall, starting in August, going through September. And the gray lines are the lows, the daily lows, and the golden lines are the daily highs. And so what we're seeing here, just wanted to show, this is focusing on conditions that are good for red color development. That's something we focus on a lot here in Michigan. And so the red bars are that range where the daytime temperatures should be in that range for good red color development. And then the blue bars show the nighttime temperatures that you want to get red color development. And you can see here at the end of August and early September, we had a really nice cool period, which helped our red color develop quite a bit on Honeycrisp. But right after that, in September, we jumped back up in temperature up into the 80s. And then you see later in October, temperatures are up in the 80s, and then it really drops down in early October. So where we think about those cooler temperatures are important before harvest, we actually had a nice window where we had some red color development, or good weather for red color development. And the average harvest date in my area for Honeycrisp was September 19, but that was hot. Those were hotter conditions. So we had to watch fruit maturity because it was advancing quickly. So I bring this up to just think about if you're looking at a weather pattern that's coming up and you see high or low temperatures in the forecast, um, when we harvest and how we harvest, I think makes a difference too as we think about fruit quality. So as a grower, if I'm thinking about it as a grower, do I harvest, in the cooler temperatures before it gets really hot? What if I spray retain? Does that mean that I'm now delayed after the warmer period into the cooler period? Or if you're spraying harvest, or you have a later variety and you see this dip in temperature coming later in October. So that gets pretty late for us, those late varieties in October. But I think these are all some of the challenges that we think about in the fall, especially. So just some thoughts for discussion. So I wanted to put up a few other things of what we're seeing in the fields that we think are related to heat, although there are other factors too that we're talking about and researching. But this is lenticel breakdown here. This is in Honeycrisp. And so one of the things that I've been looking at in orchards is if this is related to heat temperatures, again, that temperature differential that the fruit is experiencing when we see damage, what environmental conditions, humidity, are we seeing damage start to develop? And this was an example of Honeycrisp as well, where we saw sunburn here and cutting into the fruit. It was very brown inside the flesh. So that's something that we've been seeing here in Michigan. And then this internal browning, just that breakdown. So this was a situation where we had fluctuations in temperature in the fall, and there was a cold period that happened after a really warm day, and the grower harvested after the cold period and ended up with some storage disorders. So it's hard to say this was temperature related and heat related, but certainly those are things that are on our minds. As well as fruit quality, fruit firmness, and the amount of sugar that's in fruit. So these are, I know as an extension educator, these are things that I think of, but as a grower, I know it's much more prevalent on your mind. And then I wanted to bring up cherries too. I know we have a lot of sweet cherry growers, and I know that the heat, especially out west, that's been something that's really impacted sweet cherry quality. There's a really nice article that Washington State just put out about cherry disorders related to heat stress. So these are some examples of what can appear for sweet cherry. We've definitely got more experts in the room to talk about this, like Bernadita, but for across crops, across tree fruit, this is something that we're going to have to really grapple with as an industry. So I will stop there and let our next speaker talk about weather.
Thanks so much, Emily, for getting things started there. So I would like to introduce our next speaker. Excellent. I'm already seeing the screen coming up. So welcome to Kirti Rajagopalan for joining, and you can take it away. You might still be on mute.
Can you hear me?
Yes, we can. There you go.
Sounds good. I'm just going to find the laser pointer. Just give me a second. Got it. All right. Hello, everyone. I'm Kirti with the Biosystems Engineering Department at Washington State University. I'm not quite talking about weather, but more about the climate side of things. But obviously, weather and climate are related too. And I have some results here from recent work that's looked at trends in heat stress exposure in apples and some implications from that. And I wanted to start out acknowledging Supriya, Matt, and Bhupi from my lab, who've led a lot of the work related to the figures that I have here in the next few slides. So this is focused on just sunburn risk to Honeycrisp. And Emily mentioned different kinds of sunburn. So I wanted to clarify this is related to sunburn browning specifically, and looking at fruit surface temperature thresholds and how often we exceed that for the Honeycrisp variety. And there's a lot in this figure, so I'll walk through what's there one by one. So on the left side here is Washington State, apple production regions, and on the right side is from the eastern US. So Michigan, New York, Pennsylvania, and then parts of Virginia also shown here. There's historical annual sunburn days on average for 1980 to 2010, and then 3 periods looking out into the future as columns. And so in general, the message here is in Washington State, there is some sunburn risk that we've historically experienced. And that's increasing in severity. So red means more sunburn days per year. So you see more reds in the climate projections. And you see more areas with darker reds. And in the East Coast, there's not as much risk as compared to the western side of the US as compared to Washington as of now, as everyone knows. But you start seeing emerging risks more often as you look out even the next 20 years or so. And that storyline is true across 2 different kinds of climate scenarios going into the future. The bottom one here corresponds to more warming in the future with more greenhouse gas emissions. And the top row corresponds to lesser warming because there's some mitigation of greenhouse gas emissions. But the actual number may vary and there may be uncertainty around it. But as expected, more areas experiencing sunburn risk and more intensity of sunburn risk. And this is for the Honeycrisp variety that is more susceptible to sunburn browning with a lower fruit surface temperature threshold. When we look at the same thing for the pink lady or Crips pink, trying to move my slides here. This is pink lady. So you can see this is less susceptible. So you see the colors are less dark here, both for Washington State and the East Coast. But even the less susceptible variety is seeing some risk emerging in both the east side of the US and the west side. And that those maps in the prior slides were corresponding to no mitigation to sunburn. And here we look at netting as a strategy to mitigate sunburn. And there's a time series here. X-axis is from historically 1950s, looking out into the future until 2100. The top row is for Washington State apple producing areas, and the bottom row is for the eastern US apple producing areas. And there's the higher warming scenario on the right here and the lower warming scenario on the left here. And there's 3 lines and 3 colors that you'll see. One is with no netting. And then we also did some model simulations looking at two kinds of commercially available nets, one of which that reduces radiation by about 20%, and the other that reduces radiation by about 30%. And both of them lead to reductions in wind speed, which are assumed in the simulations as well. So we focus on Washington State. If you look at the historical period, yes, there is some sunburn risk, but it's by and large mitigated fully through through netting as an option. But even when you look at netting and how air temperatures translate to fruit surface temperatures and the different meteorological conditions and how they affect the fruit's energy balance, there's competing mechanisms there. Some lead to increases in fruit surface temperature, other leads to decreases. And overall, when you put them all together, there's a limit to how much reduction in temperature netting can offer. And so even as we go out, looking out the next 20 years or so, we see this situation where netting, yes, still reduces fruit surface temperatures and the sunburn risk, but is not able to mitigate fully to zero. And that's exacerbated as we go further out into the future. And again, it doesn't, between the warming scenario, things may be different with higher level of sunburn risk or lower level, but the storyline is generally consistent across all of the scenarios, and of course less prevalent for the eastern US than Washington State. But netting alone as a strategy is unlikely to work even in the next 20, 30 years, and other strategies in conjunction with it is something that'll need to be evaluated, especially for the more susceptible varieties. When we move to the less susceptible varieties, this one is Scripps Pink. Again, there's sunburn. The netting seems to work well, even in the next 20, 30-year situation time frame, but perhaps not so much after that. So some risk even in the lower susceptible varieties that continues. And so with that, one of the things that we've been looking at is evaporative cooling. It's used currently in Washington State as well. It's a mitigation strategy that works really well. But using water for cooling means there's additional water needs. And especially in the Western US, where places are already water stressed, there's questions around, is there available water for additional cooling? And some people have access to the water rights, others don't. If you don't have access, how do you get access to it? If you do have access, then using that water means there's trade-offs with other uses like flows for fish. So how do we manage all of these competing uses? So we have an ongoing project that's looking at that particular aspect. And the reason we are interested in looking at it is historically, when we think about irrigation demands and how watersheds plan for it, we focus on the crop's ET needs. And so the bottom two lines here that you see in these figures for Honeycrisp and Crisp Pink relate to the crop's ET needs and how that's expected to change in the future. And you can see that they are pretty much flat lines. We don't expect that much of increase in crop ET because with warming, plant growth is accelerated and the time to maturity tends to shorten, and the post-senescence period with less water needs become a larger part of the growing season. So this is kind of the storyline that we have been working with in terms of planning for water in Washington State and in general in the Western US. But when you add in additional water needs for additional evaporative cooling, the shape of those lines change. So the total water needs change from not much change to a significantly large increase. And that's the same for even the high susceptible variety and the low susceptible variety. So there's need for more water that we need to plan for that we're not currently planning for. So that's the aspect that we are working on addressing right now. The other thing is that's just additional water in terms of sunburn browning. But as Emily said, temperatures in fall matter too, especially with the red color development. So what we see here is for the US, the top figure is showing the climatology of fall temperatures, or average fall temperatures. And if you focus on the apple growing areas, you see, yes, there's few days where the fall temperatures are higher than what's optimal for red color development, and more so in the eastern US. That's more of an issue there currently. But if you look at the trends or changes historically in the last few years, you see large positive increases both in Washington state and in Michigan and New York areas. And that's more easily seen in this figure that's pulled out Yakima County, Kent County here, Wayne County in New York here, and Yakima County in Washington. So we can see increasing trends there. And anecdotally, we've heard from growers here that using cooling as a mechanism for color development is something they're thinking about, not something that they need right now, but thinking if this is something that's in the works in the future and something to plan around too. So basically, for managing extreme weather, there's likely more water needs. And especially in the Western US and also in the East, we are looking at more droughts and, more importantly, more frequent back-to-back droughts. And so the darker colors here means more frequent back-to-back droughts, and you see a lot more in the Washington apple growing areas. So together with all of this, our interest is in looking at, okay, how do we manage this heat stress? How do we manage the additional water needs for that? And what kind of varietal adaptation or moving water across different crop groups in a water right environment can we look at to make ag production viable? And that's what I had.
Excellent. Thank you very much, Kirti. So our next speaker, I'd like to introduce Jeff Andresen, is the professor in Department of Geography and state climatologist at Michigan State University. So Jeff, if you are able to share your screen.
Oops, this is one from earlier today. So sorry about that. Get rid of that one and go back to the proper. All right. All right. Sorry for that.
No problem.
And thank
It's
you
looking good.
very much. It's a pleasure to be with you today. And I think Kirti did a well. Hopefully, can complement some wonderful information. I'm going to probably focus more on the Great Lakes region on trends here. There are some very, very distinctive weather and climate trends, and many of them are relevant here as we consider heat injury, heat stress in apples, and I'll talk about that. But in essence, one of the take homes is, and this is true to a large extent as well in the Northeast, which we'll hear about a little bit later. But our part of the world is getting warmer and wetter, and it's just that direction we've had climate-wise for the past few decades. And I'm going to start with just an annual temperature, just to look at when you add everything together. I'm going to focus more on the warm season here in a second. But if we just look at the annual temperatures, take everything together, this goes back to the end of the 19th century. We're going to show you a couple time series here, just again to illustrate the trends. And the black dots are the individual years values, and then the red line here is a moving average, which is fit to the data to smooth out some of the noise and give us the longer term decadal type trends. The world has warmed up about 1 degree Celsius here in the last 150 years, and much of the U.S. has warmed up at least that. Here in Michigan, we're a little bit over that, but it's important to note that not all of the warming. We've had about 2 degrees warming here just in the last 50 years, that it's not symmetrical. It's more of it has come in the cold season of the year and at night. Our minimum temperatures are increasing more rapidly than our daytime temperatures, and it's actually fairly so the diurnal range, the difference between the two, that's decreasing, and we see that in many parts of the world, not just here in the continental U.S. But you can see here again with this that obviously the warmest years on record here are those in the last decade. It's also becoming wetter. This is the same type of graphic, except now we're looking at total precipitation, which is all liquid plus melted frozen precipitation, everything together, how much water came, and the same time frame up through the end of December of last year. And again, there are some temporary or changes and some noise, but ultimately the trend is definitely upwards, especially over the last 50 to 70 years. It's really here in the Midwest. It's been getting wetter ever since really the Dust Bowl era of the 1930s. You can see that back here. That's the benchmark driest decade on our historical record. It's true across much of Central North America as well. And in the last 50 years here in Michigan, we have added on average about 10 to 15% of our annual precipitation total, again, as an average increase. And to translate that, that doesn't sound like that much, but that translates to about 3 or 4 inches of extra water we have now that we did not have on average just, again, a half century ago. That is a lot of water. That's a major, by any climatological standard, that's a huge trend. And I think the numbers from the Northeast may even be larger than that, but this is a very, very distinctive signal in our climate here in the central and in the eastern part of the country. Of course, to get more annual precipitation, there's 2 ways you can do it physically. One is to have more days with precipitation. That's happening. So we're getting an increase in the number of wet days. It's increased sometimes on the order of about 30% more days with measurable precip now than, again, half a century ago. The other way to get more precip, of course, is you have more per event, and that's also happening, notably with extreme events. And I think Kirti mentioned this. This is one of the, again, and it's actually a very, very problematic trend in a number of ways. It's not just agriculture, but infrastructure, you name it. It's these heavy rain events are increasing in frequency and in magnitude. And so 1 inch, 2 inch events, all of those are increasing. And then collectively, that is what you end up with, again, about somewhere, again, 10 to 15% more precip now. And the trend really has shown no signs of letting up yet. You'd expect it at some point in time. I want to go back, though, to temperature now, because it's really sort of the focus, one of the foci here of what we're talking about, because there's some very interesting nuance if you look at the data here. And I mentioned, yes, it's getting warmer overall in our climate. And the summer, if you look at the summer months, June, July, and August, those are the lowest. They're warming, but they're the least the less increase than there is certainly in the winter or in the shoulder seasons of spring and fall. And more importantly, if we actually look at these temperatures, and I mentioned their decreasing diurnal temperature range. So here I'm taking temperatures for the summer months, June, July, and August, sorry, get them out of the southern hemisphere here. And I'm splitting them up into the maximum temperatures on the left-hand side here in the red and the minimum temperatures on the right. And the Midwest is it's a lot unusual or unique in this regard. So if you look at the maximum temperatures in the summer here over the last 100 years, there's not much, it's sideways. There are even parts of the Midwest, notably in the middle of the Corn Belt, and we'll come back to that in a second, where the maximum temperatures are actually decreasing. And that, if we look at internationally, it's one of the few places in the world. Everywhere else, maximum temperatures are increasing. It's true in the Western U.S. It's true in the vast majority of the world, certainly temperate latitudes. But if we look at the minimum temperatures here, and let's switch over to the right-hand side here, most of the warming that's occurring it's occurring at night with our minimum temperatures. This is also related to humidity, because humidity moderates the amount of cooling that takes place on a diurnal basis each day. And it's another part of this puzzle, the integrated pieces at looking at heat stress as well. Vapor pressure deficit's one of those variables, but because as the temperature warms up again, theoretically, the air can hold more water vapor, and it's not linear, it's exponential, it goes up dramatically. And at least so far, with the warming that we've seen, there's just more water vapor in the atmosphere now than there has been in the past. But again, these maximum temperatures, and this is a fascinating one. Why? Why is the Midwest different from everywhere else? And the answer, very, very likely, some great research was done on this in the climate research community. And what it all points at is the landscape. And the one covered by monoculture, corn and soybeans, millions of acres, collectively, which consume just tons and tons and tons of water in transpiration, evapotranspiration, but especially transpiration, because the other factor is that over time, those monoculture systems, one of the big differences is the populations have increased. The amount of evapotranspiration that's taking place has also increased. So a huge amount of water is going into evaporation, energy is going into evaporation of water that could have gone into heating the surface, into the sensible heat surface. So we actually have, and this occurs on a large enough spatial scale. In the Midwest, it is large enough and it's dense enough. It actually can cool the climate during the day, and that's physically what's happening. This has been observed in a couple of other parts of the world, but it's always intensively cultivated agricultural areas of the world. The Midwest is one of them. So we're different, and the big question is, as we continue to warm up, how long, with this external forcing, which is related to, of course, greenhouse gas concentrations in the atmosphere, how long can that leveling off or that stable temperature, because it has and it's directly relevant here for the topic that we're talking about. We're just not seeing the increases in maximum temperatures yet. All of the model projections suggest that will happen, but the question is, well, when, or why hasn't it happened now? And again, and it's another human related factor. It's landscape, the management of landscapes, which is intriguing, but it's another, it illustrates how complex that this is. You have to look at all these different factors here. One other aspect that is also changing, and it's indirectly related to what's being talked about here, and that's the seasonality. And as it's getting warmer, we're seeing the first freezing temperatures of the fall season. That's up here in red. And now we're only looking at the last basically 40 years here in this series. But this is a very consistent trend across almost all of the Midwest. And I think the Northeast, but certainly in the Midwest. But the date of that first freezing temperature of the fall is getting later and later with time. And so the calendar day here, day 1 is January 1st, day 365 is December 31st. So we're using that system here for our dates. And that first freeze of the fall, 1 to 2 weeks later on average now than it was 30 or 40 years ago. On the other end of the season, the last freezing temperatures of the spring, so 32 Fahrenheit or less, that's getting earlier by about a week to 10 days. And if you look in the middle, your frost-free growing season between the last spring and freeze and the first fall freeze, that's here in the green, look what happens. It jumps. And this is again an amazing trend climatologically. You just typically don't see things this large, or trends this large. But we added at least 3 calendar weeks of our frost-free growing season just in the last 40 years. And again, well, why are we talking about that with heat stress? And the answer is and Kirti mentioned this. It's about the phenology, because we're shifting the crop calendar earlier in the year. This is looking at simulated first date. This is for tart cherry. It's not apples, but or pears. But we're seeing our spring warm up is occurring. The seasonal warm up is occurring now, a few weeks earlier on average than it did 50 years ago, and it's pushing the whole growing season earlier. So that has to be taken into account as well, relative to what we've seen in the past. So it is indirectly, it's also a factor here. Kirti mentioned this. Again, why do we care about this for fruit and so forth? I use this for a class, but it's about the energy balance. One thing to remember, though, too, it isn't just the air temp. The air temperature is important, but it's actually the radiative temperature of these apples themselves, and that can be very, very different. And of course, in these injury events, it's much. And I think Emily mentioned that at the beginning that the skin temperatures, because of environmental factors such as strong solar radiation, lack of mechanical sensible heat loss from lack of wind or lack of contact with the atmosphere, all these things act to elevate the surface temperature, and that's when you have the problems relative to its environment. And so it's not just the air temperature. You have to look, and again, and Kirti showed that very, very well. So I'll jump here. Let's look at some of the factors. And again, we saw some of this from the West. The frequency of hot days, this is defined as 90 degrees Fahrenheit or greater in much of our region. That's still pretty level. And that's one that's projected to go up, but it really hasn't. So and actually you can almost argue here statistically that this one actually declines. So this is from Grand Rapids in western lower Michigan. So that one we're not seeing much yet here, but other parts of the world that definitely is true. Warm nights, different story. This is clearly increasing. Kirti showed this as well for several locations. This is also Grand Rapids, but this is true almost everywhere in our region. And you can see that it's not small. It's a significant increase, maybe 30–40% increase in these warm nights. Here we've defined that as 68 Fahrenheit or warmer. So that's also increasing. And again, when we think about color, and quality here, these are related. So that clearly is a problem, and it is happening. It's observed, and it's projected to go into the future. What about humidity? What about moisture? Well, this is a little tougher because the data we have, the observations we have for humidity, the technology's changed. It's more difficult to put together trends. But we do know there are some pieces of this we do know. This is looking at trends from the late 1940s to the last 70 years in dew point temperature. Dew point is a direct measurement of how much water vapor is in the atmosphere at a given time. And the reds here across the U.S. are all increases. Blues are decreases, and there's always going to be some variability, but by and large, the vast majority we're seeing increases in that. So as the air warms up, it can hold more water vapor, and that is happening. So far, that is increasing. So the amount of water vapor is increasing, and here's the specific humidity trends. It's not relative humidity. This is actually specific. This is how much water vapor physically is there, and we can see it across our region. The four variables that are important here. The top one is precip that we're looking at here. So, and I mentioned it's getting wetter. You can see that this is over the last 60 years across the upper Midwest. Here's the one that I wanted to show, and it's important: the vapor pressure deficit. Okay, what is that? Well, you've heard this, and this is a major factor in some types of heat injury, sun scald, and so forth. And it indicates how much difference there is in the atmosphere at a given time, how little or how much is the amount of it's like the relative humidity, how much water vapor is there relative to what the air could hold. The larger the deficit, the greater the atmospheric demand for water vapor, and the more stressful it is on, a plant or anything that's trying to keep water. So the higher the water vapor pressure deficit, the more stressful it is. That is actually decreasing in part of our. So that one is sort of contrary, and it's because of the increased precipitation and also probably the increasing humidity. But that factor actually in terms of heat injury here, at least for now, is decreasing. It is projected in the future though to increase, to get larger. And I think some of Kirti's projections for the future definitely take that into account. But so far, looking at the observations, that one is a little different. Our vapor pressure deficits have actually decreased. Specific humidity is the third one here, and that is actually increasing over time. And finally, PET is potential evapotranspiration, describing the physical atmospheric demand for water vapor from what a plant or a fruit, whatever's there, how much physically is drawn by the atmosphere for those physical conditions, and that is also decreasing. It's related to the precip trend primarily, and the fact that those daytime temperatures have remained steady. How long that goes on, though, it's not clear, but it's different from many parts of the world where we've already seen increases in potential evapotranspiration, but not so far in the Midwest. One last one here too that's also very, very important, solar radiation, because of the addition, the source of the energy that drives all this process here, it's increasing. So that one is also suggesting this, and this is divided here. There aren't that many good quality solar radiation sites across the U.S., but we're looking at the eastern side of the country or the continent and the western side as well here on the right-hand side, and it's increasing in both. Interesting. There's some interesting reasons behind that, even though cloudiness in some parts of the U.S. is increasing. So you'd say, well, how can you increase solar radiation if the clouds are increasing? And the answer is the Clean Air Act. It's because the atmosphere now is cleaner. There are fewer sulfate particles in it than was the case 30, 40, 50 years ago. And so we're actually seeing some increase related to, again, to human activity or human action, which is intriguing. But the bottom line is here for heat injury, we see a little bit more solar radiation getting in, and that, of course, that's potentially a negative thing for our heat stress problems. If we do some statistics here in Michigan and look at the frequency, and Kirti showed this really well, it doesn't happen that often when you line up the weather events. This is looking at sun scald, where we're concerned about high air temperatures, high solar, and lower wind speeds together collectively. And what the frequency, how often do these conditions come together? Well, these are box and whiskers plots, and actually the greatest month here frequency wise where all these things are met, these conditions on the left hand side, is in the month of June. So fortunately, that's a little bit ahead of. We'll focus on July, August, and September here in just a second. But again, this does not happen very often now. This is also a site in the southwestern corner of Michigan, so it's really sort of on the southern edge of the primary apple production area in the Great Lakes. So it's even less than this as you go to the north. But it does happen, and it's primarily during the middle of the summer, not the late summer and the fall. The trend of these, looking at that, it's actually, and this is mixed. We see some sites where it's mixed, but it's actually at this site at Benton Harbor, it's actually declining. So again, the atmospheric conditions all together here, and it's related to some of those factors I just talked about. That even though the solar is increasing a little bit, that daytime temperature is a big factor. But if we actually put those things together, it's a rare event. It's a little bit even less common than it has been in the past. But that projections suggest that will change in the future. And so I'm going to summarize here and looking forward to some discussion about this. But warmer and wetter is where we've been, and it's where we're projected to go over the next couple decades. One very, very important factor, and again, Kirti mentioned this, it's critical, and that is as the climate warms up in the future, the atmospheric demand for water is going to increase, and the potential that potential evapotranspiration is a critical variable. It's a critical variable for this issue because water is a great moderating factor in nature and the environment, but all of the rates of PET are projected to increase significantly, 10 to 30% here, probably in the upper Midwest. And so as that happens, the likelihood and the risk of this problem will almost definitely certainly increase. But I wanted to show what we have at least at this point in time, and offer some historical perspective. Now I'll stop there and hand it off. Thank you.
Wonderful. Thank you very much, Jeff. That was very interesting. So it's it's rather unfortunate but quite fitting as we're talking about weather extremes that our next speaker, our scheduled speaker, it was experiencing some severe storms, so she's lost power and is unable to make it. So we're going to have to jump ahead to our final speaker. Lav, I'm sorry to put you on the spot here. Hope that you're ready to share the screen. I'd like to introduce Lav Khot. He's the professor and director of AgWeatherNet in Biological Systems Engineering at Washington State University. So when you're ready to share your screen, go right ahead.
Okay, let's do this. Can you see my screen?
Yes, we can.
Perfect. Well, this is good because we're talking about climate and how extreme it is going to be. I'm going to cover a little bit about what tools we have to monitor and manage the heat stress, I guess, right? And First off, of course, I mean, I saw some of you are already using AgWeatherNet and National Weather Service and the New York side of things, the New York Mesonet. So I'll just say that, in state of Washington, we of course have the weather sensing network, and that's where we'll start, I guess. This is one of the oldest and largest network, and again, since 89 we are doing this. To 2006 we standardized, and now we are in the rebuilding phase, I guess, right? And the map you see on the screen here is today's, just 15 minutes back. You can see how the heat is, flowing actually. And we go down also, we have the stations coming from the Hood River area. You can see the heat wave that is coming from that area too. So anyway, so that's where I think we start. And then again, besides our network, what you see on the right side here, I should probably get a pointer. I know how to get it, or I'll just not. Yeah, you can see, like, besides our network, right? We are building towers, and this is our legacy network, but we are also accepting private grower deployed weather sensing networks. We apply same QAQC and then tie our edition support to this, right? So we have like about 138 of those stations also flowing through our network, right? And we talked about how can we be a little bit more proactive than reactive. And in that case, what we are trying to do here is, of course, National Weather Service does have the weather forecast. NDFD has that coming out for next 10 days. And we know that in Washington State, we have microclimates, right? And so what we are trying to do is take that NDFD or National Weather Service forecast, and then using our historical stations data we have, we are like trying to improve the station specific forecast. And in some cases, we are about 35% better in terms of air temperature and those parameter forecast actually. And then skill, of course, is better for next 3 days, and it kind of matches to the National Weather Service. Then once we have that forecast, actually, we are trying all the decision support tools that we have for different fruit crops there with that model or forecasted weather data actually. So of course, for frost mitigation, we have the inversion forecast, and then giving the decision on when to mix or not mix the air. The same inversion forecast allows us to estimate delta T, and then for next 3 days, we say when are the good conditions to spray or not spray. But then going back to the water and heat, actually, right? So the same forecast actually for given station allows us to estimate the ET, I guess, right? You can see in the top here for next few days, we're already estimating the ET, and so growers can look at that and adjust their irrigation schedule. More specifically for the heat stress, we have our group is in this research since 2014 timeframe, I guess. And now we have what is called a random forest model that takes the weather data and the fruit size and estimates fruit surface temperature. One of my colleague, Dr. Troy Peters, he also has developed energy balance models. So that model is also tied to this weather data. And so then we go and estimate the fruit temperature or fruit surface temperature for next 10 days. It resolves at 1 hour scenario. So growers again can use this, and this is trained more for Honeycrisp. Of course, that is a base, but then we can, you can see which days the heat stress is coming and prepared with your resources, and given day, of course, you can also see how this is going to change, and then plan mitigation. One of the good thing about our network, we switch from 15 minutes to 5-minute data. So this is high resolution data coming. So there's more proactiveness can come through this actually, right? So that, and then going from there, of course, everybody has smartphone devices now. So we also have the AgWeatherNet app, just released last month, actually updated version. And so a lot of folks have downloaded. If not, you can download here. So there, our app is unique in the sense that it not only shows the weather data, but also decision support tools. For example, here what you see is for apple or grape, you see the fruit or berry temperature. And if you click on this, then you get next 2 days hourly resolution of the fruit temperature. So you again become a little bit more proactive there, I guess, right? Then if you click on this bar here, then we have other tools for heat stress mitigation. One app that we have released is on-crop AI. And I'll talk about that a little bit later. And also we have on Smart Farms platform that is again helping growers to monitor and mitigate heat stress. I'll talk a little bit about that as well. So, but that's going. This is our anchoring app to some extent. So, the on-crop AI is the app that is it does two things. One is, of course, use station-specific forecast and the models that I spoke of and estimate the fruit surface temperature for next 10 days at hourly resolution. And then we have color coded it, so it's easy to, and bilingual, of course, and then you can just see which day stress is coming and plan mitigation. It also allows you to connect this is a thermal infrared camera that is there that you can connect to this, and then it runs the machine learning behind and then segments the canopy and fruit and then get hottest 20% pixels of the fruits in the zone and then say this is what going to be the fruit surface temperature for you. And then also it does give you the canopy temperature. And because we have RGB there, it also tracks the color progression. And then we have this done for the apple and grapes, and we are now adding blueberries into this actually. So this is also the freely available app that one could use for planning the heat stress mitigation scenarios. In terms of other tools, like I'm sure some of you use these thermopens or heat guns and our thermal infrared camera. So we looked at, because we had last year field day and somebody asked this question, which tool I should use. It depends on how much money you want to invest in this, right? And so the best is to use thermal camera because it is spatial. And then, of course, if you use our app, then you're getting the worst case scenario, the top 20% pixels. But if not, if you just have a thermal camera, then it shows you the spatial aspect of temperature distribution. If not, then you will resort to some of the other low-cost technologies. And then also in the process, just want to say that when we have these thermistors insert in the fruit, um, at about 6 millimeters, we saw that there is a 3 degree Fahrenheit difference between what is fruit surface temperature to what is the internal fruit temperature, just for the perspective there. Then going into like continuous monitoring and management potentially, right? So AgWeatherNet, of course, has our network and private stations, but this season we have launched what is called Smart Farms. So what Smart Farms is that is the DIY where you can buy soil plant weather sensors and use what is called long range wide area network type approach, where instead of each node, sensing node, having its own cellular connectivity, you send this data to this node, the gateway, LoRaWAN gateway, and within this 10-mile radius, and then with one cell subscription, you pull all the data and then send it to us actually at AgWeatherNet. And then we clean the data, and then again, we have the platform build. Right now, we are in monitoring, and this season, we are hoping to manage temperature-based scenarios. We piloted this. We had support from Washington Tree Fruit Commission through Smart Orchard Project. Bernadette is on the call here. And then we have another pilot like project where we are just talking about heat stress and scaling this up. And I think Bernadette is keeping us busy because we have about 18 sites in Wenatchee, Okanagan, and Yakima Valley that we are trying to add there this season. So again, this is coming from 3 years of research, of course. For irrigation management, we try to use soil plant weather sensing, and then there are commercial solutions like, for example, Swan system has a climatic model. And then, if we push those data-driven models, we showed that you could save about between 20 and 52% water. And this is coming from two different managements. You can see there are two different managements, year one, year two, for the same block. So of course, management will have its effect, but in that scenario also, at minimal, you could save 20% water and get the same quality fruit, I guess, right? In terms of heat stress, again, the same scenario with the two different managements, right? And in this case, again, the baseline for irrigation, we didn't control the irrigation. Grower did what it's supposed to for both blocks. But if you use sensors, and like, for example, the IRT sensor here that is getting at the canopy or fruit temperature, or, fruit surface temperature that we did, we could save between 46 and 50% water there, right? And so this is what we are trying to, scale now actually. And these are some of the other tools that we have. I'll not go there. maybe I should just go into the platform itself if I could, and then show this how it works. Actually, I will try to show this. Maybe I'll share my screen itself. Then let's see. So this is, can you see the AgWeatherNet portal? Okay, perfect. I see them. So thank you. And so this is AgWeatherNet portal, of course, and this is today's current last 5-minute observation. But if you go to networks, this is the smart farms that I was talking about, and this is, oh, this is coming, I think, from Okanagan. But yeah, I saw. I will just go to Matwa Smart Orchard there. So this is our Smart Orchard test bed that is there. And this is the dashboard, of course. And then you can, this is behind the login. Individual grower would have its own login and so forth. So for this block, for example, we have this is the sub block, and then their grower, and in this case, we have added some sensors, and grower has added some sensors. So, for example, if you click on one node here, I should show you, like, this is a snapshot here. You can get quick view of soil moisture and the air temperature, and fruit, or in grapes, you'll get a bud temperature data there. But this is actually current measurement. I will just go here, and I think Jeff talked about vapor pressure deficit. If you have that sensor, we have the Atmos 14 there, so we have vapor pressure deficit, we have the soil moisture, for example, all that is there. I guess you can see all this. And then you can, of course, go back. So, for example, I want to go last 3 weeks and what I did actually. So you can see air temperature, vapor pressure deficit, your irrigation events are coming here. I can go one more week back, for example, to see how where you did irrigation and how the soil profile is changing. But importantly, you can see the air temperature here, I guess, right? And then today, for example, it is at about 90.7. But then you can also, if you have added fruit thermistor there to get the fruit temperature, you can see the real-time difference between what is a fruit temperature to what is a air temperature. Actually, you can see here, for example, yeah, I mean, worst case scenario would be somewhere here. You can see air temperature 81, but fruit is at about 102 °F, something like this. So this is real-time monitoring, and so forth, right? So you can use this. And right now, what we're trying to do is have growers, of course, use time-based threshold, like start scheduling the cooling at 11 and then go cyclic, or if it's a fogging type scenario, it's go all day. So we have that schedule, and we are also having built temperature-based scheduling, temperature threshold-based scheduling, that we are pushing this. And so first, of course, because of the nature of the technology and the cost involved, we are working with 3 different controllers. First controller, that is a low cost, mild side, that's what will go in first, and that's what our project is trying to push for first. And then we have, of course, a lot of growers use Nelson twig, and also there is a Wisecon is having drop control. So we have planned to integrate those controls. So what will allow is the growers can do their DIY deployment of the sensors at given block, and also then send the schedule to the controller, and then real time actuation happens. And so as of now, of course, we have, like, as I said, 18 Apple Smart Orchard test beds that we are trying to do, and then we have 3 in grapes, and then few in blueberries that are coming up as well. And just to say the success story, last year we did this for grapes, and then same grower now has about 50 of the blocks nearby just hooked into this smart farm. And so we see that value of course, saving water through real time and block specific sensing. And then just want to put this, that of course we have regional weather data, but if you start collecting your data, and then entity like us or anybody that you trust have this data, then we're talking about AI and ML. We need that data. I guess you need that data. So this is a step in that direction, actually. So with that, I will stop. Yeah. Thank you. Thanks for having me on this. So.
Thanks very much, Lav. Appreciate that. So let's see, at this point, Sonia, am I going to hand it over to you?
Yes.
All right, take it away.
Thank you, Kristy. So we are now going to pose the questions you have to our speakers. So I'm going to start with Jack had a question in the chat. How is the evaporative cooling managed vis-a-vis scab and summer disease risk? So water activated type diseases. I'll open it up to anyone on the panel or on the team who would like to jump in and talk about that.
Do we have a plant pathologist available? And this is beyond my but just to start, it's something, it happens here with some of our field crops with irrigated soybeans, for example, in white mold. It's a really tricky, here it's a very, very tricky situation where it's a fine line between providing the water that the plant needs and accelerating the disease risk. And obviously that's I'm sure the origin of the question, but I refer to my colleagues at Washington State. It must be, even though they're in a drier climate, but in a humid climate, this is a real issue.
Yeah,
Yeah.
you're right, Jeff. I think that in Washington we will have challenge to answer this question for the eastern side of the US and North America, because we have such a dry climate that scab is not a big problem. I'm pretty sure there's some growers in the cold that maybe can add to that, but when we do overhead cooling, we tend to not worry too much about the fungal diseases at least. So I will defer maybe to Emily if she or Mario that is in the call.
Yeah.
They have more information.
Actually, if I can jump in, or sorry, Emily, if you want to go
Yes.
ahead.
No, go ahead.
Okay, I was just going to say that I mean from an eastern side of things in Jack's Ontario, so he knows all too well about the humidity that we have here, and so scab is definitely a big concern. Oftentimes, I mean, most scab infection by the time we hit, and here we go, I'm going to be a Canadian and say 28 degrees Celsius. You can do the conversion. Once we reach about that point, then you're not going to see scab infection really being a concern. So when you're thinking evaporative cooling, it's usually when you start to get to those extreme temperatures. So the risk would be less from that standpoint. But then when we start talking summer diseases, and in particular bitter rot, because that's becoming more of an issue in the East, that's certainly a warmer weather pest. So above 30 degrees Celsius, and we could still see some infection. So it does definitely, those two are very difficult to balance, the evaporative cooling versus disease management. It's certainly something that you wouldn't do in a high pressure block if you know you've got severe disease pressure. I think some people kind of manage doing more cyclical attempts, right? That they would kind of do it in having some breaks so that there wouldn't be that leaf wetness timing that would be needed for infection necessarily. But it's a big risk when it comes to evaporative cooling. Sorry, Emily and Mario, I don't know if you have anything else.
No, that was great. I was actually curious about that leaf wetness period because that's what we track in this season. It's been really interesting, at least in my area, because we've had rain events, but it's been so windy that we haven't had long enough periods of leaf wetness to get an infection. And so, yeah, I'm glad you said what you did, Kristy. And Bernadita, I'd be curious to know how long the canopy is wet when you're using evaporative cooling out west.
That will be a question for Lab. Lab, do you have that data on?
Sorry,
A rough guess.
I was distracted. Can you please repeat?
How
What is the
long
question?
how long the leaf stay wet after the evaporative cooling or fogging system? Those are very different. We're going to talk about that in the
Yeah.
next session, but do you have records of how long it? I guess it depends. The answer
Yeah,
will
I
be
mean, it depends
depends.
on, of course, the wind, of course, and then temperature, I guess, right? But in grapes, I mean, we have done this for grape heat stress automation because for, wine grape, you want to have not much moisture going into the soil, I guess, right? So we have the leaf wetness there, and we stop the cooling when the leaf wetness sensor saturates, something like this. and that saturation happens fairly quickly actually, right? So yeah. Yeah, but we
And
could add this. We never thought about adding leaf wetness in the apple actually, because anyway you are irrigating under tree and all that actually, right? So yeah.
There were some growers, Bernadita, here who recently mentioned like somewhere between 10 minutes and 30 minutes is what they've observed. And that's the reason why they're thinking about the cycling times. Like, do you do 15 minutes on, 15 minutes off, or 15 minutes on, 20 minutes off? And as Love said, it varies by weather too, right? Like
yeah.
today's time of wetness is not going to be the same tomorrow. But what I've heard from growers here is 10 to 30 minutes.
One aspect that a number of you have mentioned that relates to one of the questions we have is about wind. Are there data regarding wind-related issues and in particular changes in wind conditions? Do we know anything about that?
I can start on that. And unfortunately, the answer is we know less. And I would say wind is one of the most difficult variables, atmospheric variables that we work with. And it again has a great deal to do with the technology and changes of technology and also the exposure of the instruments over time. It's made it very, very, very difficult and complicated to do the same thing we do with precipitation. We can't. So not much is really known with anything conclusive with wind speeds. Unfortunately, it's going to take a while. There's standardization now of the technology, but we don't have a very long time frame. So that's the reality. Humidity is a little bit better than that, but for some of the same reasons I talked about earlier. But that wind is a tough one.
Mm.
Yeah, and
Jeff, I just want
unfortunate.
to,
Go
yeah,
ahead,
go ahead,
Love.
Kirti. No,
Go
go ahead,
ahead.
go ahead. Yeah, go ahead. Yeah.
But I think I was just going to say wind is one of the really important variables too, especially for evaporative cooling. And it's something, so for example, even shade cloth netting changes the wind speed quite a bit within the orchard, and we don't have an exact idea of what that is. And it lowers the wind speed, which is not a good thing because that's going to raise fruit surface temperatures. So I think
Yeah.
knowing wind speed is really important. And, as Jeff said, this is not something we know with certainty, but I've read some studies that talk about trends over time and with generally decreasing wind, average wind patterns. And again, uh, especially in the West Coast, there have been studies that have attributed the historical warming that we've observed in part to decreasing wind and therefore lack of cooling, especially from the oceans and things like that too. And I think earlier on somebody mentioned the Midwest is a little bit different always from other parts of the country. And my understanding is the West Coast and East Coast are similar in that respect, but in the Midwest it's a little bit different and a little more complex. And the other thing I've heard about that is interesting, and I don't know so much, is places where there's a lot of wind power, wind farming, and I think Midwest is one of them too. That has led to decreases in wind speed in general that's affected. So there's a lot that's uncertain, but I think that general trend of decreasing wind speed on average is something that's potentially there.
Yeah.
Yeah, and I just wanted to say that, I mean, growers know this, right? On calm day, and we have this in Knowledge Center of our app, of course. It says that, that fruit surface temperature is going to be about between 9 and 18 degree Fahrenheit higher. But on a cloudy and windy day, of course, the difference is down to like between 2 and 5 degree Fahrenheit, actually. So the wind matters, I guess, right? So, yeah.
A big equalizer. And one last thing to follow us up on Kirti. Most of the projections of the future, and this was done with wind energy in mind, looking at this, but
Yeah.
most of those theoretical studies suggest that wind speeds in our part of the world in mid latitudes in North America will decrease with time. It won't be huge, but that's at least what the physics suggests, given the other the other changes. So we'll see. But the observations of a decreasing trend, we have those here too. It's just the confidence in them because of the reasons I mentioned. It's less.
That is so interesting. I wanted to introduce really quick. We do have a grower here that is from Michigan who I asked to be part of the discussion. So it's Dan Zamitis. He's from the Sparta area, which is a really intense apple growing region here in Michigan. So Dan, thank you for taking the time to be here. But I kind of wanted to ask your thoughts on this too, because when I talk with growers, and I live in a very windy area in the state. I'm very close to Lake Michigan, but it's interesting, and maybe the wind is coming at the wrong times because I know there have been a few really key times early on in the growing season where it's tough to find a good spray window. So I'd be curious, Dan, what you think about the wind speeds and if you've noticed any changes or trends.
Hi, everybody. Yeah, so as a spray guy, it's always too windy, right? And emotionally driven behind this opinion, I guess, yeah, I do feel like we're fighting wind a lot more than we have in the past. But there's people who've been in this industry longer than me, and it's hard to quantify.
And I
One,
just
go ahead.
want to
I
add,
agree with that. I
yeah.
think in the
So
last two seasons, it seems there's more wind to deal with, not less.
I agree. Yeah, it's been kind of a bugger this spring. I
yeah,
feel
and
like,
I
go ahead.
just to add to that, that I think that in Washington too, we feel, and again, it's more like a feeling, and maybe I haven't been enough also to say, the scientific trend, but maybe it's just the degree of that wind and in the timing that is happening. So we had a very strong wind happening 2 weeks ago, so it very could damage the fruit quality in cherries, especially Rainier type of cherries. So maybe we feel it more because it's in a specific time window that is damaging and affecting the crop regardless. And I felt that it was becoming stronger, but again, no scientific data. So that's why we post the data the question to the experts.
We have the data. We just need to analyze, I guess, now.
Yeah, please do.
Well, there's
Another
There you go.
project
different things at play there too, because when we studied a lot of the windmills and getting on board with wind farms and wind power, they're talking, the wind on the ground is not what they're looking at when they're looking for good sites for windmills, because they're looking at what is the average wind speed up at 90 meters off the ground. So what data are you looking at? Are you looking at the surface wind, or are you looking at the climatological wind up 100 meters up off the ground? What's changing?
By default, and you're absolutely right. The wind energy is different, but everything that we use typically, it's because of aviation actually, and the international standard is 10 meters, so 33 feet. That's what it is now, but it hasn't been that in the past. And so some were taken on the tops of buildings in the past, and some were taken in someone's backyard. And that makes it really difficult. But as you know, the farther you get above the surface, the stronger the wind's going to be. That's just the way the atmosphere works and that part of the atmosphere. But most of what we're talking about is the sort of the standard. And 10 meters is not standard for human beings, because at least last time I looked, there were no 10-meter people. But it's done because of again, flight operations. And that decision was made back in the middle of last century. And it's continued till now. And so that's what our measuring standard is.
Yeah, Jeff, I just want to say, that's the reason we have like Washington, and of course, and Oklahoma and other Maisonets having towers that have the wind measurement at 33 feet, right? So, yeah. And because growers have wind machines, that they also want to know temperature inversion and also the wind aspect
Right.
at that height. So that's where our Maisonette towers are, that we are putting how the sensors. Yeah.
And that's we're doing the same thing. And we also our standard measurement is at 3 meters at 10, because we want it to be closer to a crop canopy or something that's representative, and 10 meters is less. But for the frost control, no, quite you really need to have it.
So I would like to follow on the same idea, but maybe switching from the wind to the temperature. I think, Lab, you have done quite a bit of work in relation of the in the orchard data collection and the tools that growers might be using inside the orchard, and how that compares or how that is represented by the outside sensor or monitoring tools. And can you speak a little bit about that?
Yeah, I think that's a good question. So the Washington Tree Fruit Commission had funded this Orchard Effects project to us, I guess, to AgWeather Network, and we have done this for I think 3 years and different modern orchard system architectures. And of course, it lot depends on how you're managing your orchard blocks. But overall, um, in terms of the humidity, for example, our data shows that the humidity inside the orchard block is between, I think, 9 to 27% higher than what you get with open field weather data, I guess, right? And the temperature wise, it's the same thing actually, because of the canopy that is there. And I have numbers in degrees Celsius, by the way, 1.9 to 4.4 degrees Celsius. I need to convert this to Fahrenheit if somebody could convert. So I mean, definitely the orchard has its own effect on the weather variables. And this is again going back to using the models to decide and actuate things, right? So if you have a model like fruit surface temperature model that is developed on open field data, then you probably need to consider these orchard effects. And that's why, when we are doing machine learning models, we have two different types of models now. One that is open field weather data driven, and other one that is in orchard data driven to some extent, and things like that. So yeah, yeah.
One
Following,
thing I find interesting with that, and Love, I know we've had email discussions about some of this too. Sometimes when we look at fruit surface temperature models, we find that they better match observations when we use the open field, the outside orchard temperatures, rather than the in orchard temperatures, which is a little weird. Like we would think the in orchard temperatures would give a better estimate of fruit surface temperatures. That doesn't always happen. So I think this underlying question of like we don't fully understand or explicitly put in a model all of the energy balance concepts that come together in making this happen, right? Like that question is still there and something that needs to be resolved.
Yeah, and I think that's where like there was a slide, I think Emily had a slide where thermistor was in the fruit, I guess, right? And we are doing a lot of that. So having more of ground truth data of such, and then doing like more robust modeling, I think that's where we need to go, I guess, right? And I'm hoping that our commission project with 18 site would provide us that data for multiple years. We'll see. Yeah, yeah.
That's
maybe
so surprising. Sorry, I was just wondering if you had theories on why that would be. Yeah, that's really interesting.
I think Love might have ideas. I can speak to the specific examples that I have seen. I think part of what happens there is when we take measurement or when the data that we have available that's taken within orchards doesn't often take all of the meteorological variables. It takes some of them, but not everything. But from an energy balance perspective, everything needs to come together, right? All meteorological variables affect other meteorological variables. If you take some in orchard numbers and some outside orchard numbers, it doesn't work. In those contexts, we're often better off taking all outside orchard numbers because at least they make sense together, right? The way in which they affect each other is all captured. So that is my theory for the few cases that I've observed. I don't know if that's exactly how it's playing out or not. And I think the other thing with that is with all models, especially data-driven models, they can get the right results for the wrong reasons. And we see this all the time, right? And So I think that's where, like, not purely relying on a data-driven model, but also making sure it has the biophysics embedded into it, where we're not just creating energy, but it's all matching up well, I think is important for answering these kind of questions.
Yeah, and that's why I
Yeah.
think when we model it, I guess, right? And of course, energy balance has its own sensitivity issues with what you consider, I guess. So our models, that's why we are trying to get fruit size, I guess, for example, right, entered there because fruit size would decide, how much energy you're absorbing or desorbing, I guess, right? Something like that. So yeah.
Uh,
So there is no clear-cut
It's
answer on this, I guess, right? We'll see. Yeah.
more
before I
work to
before
happen.
yeah.
Um,
Before
sorry.
we give the hand to Garrett that I had the hand, I just wanted to just pose that I don't know how these studies were done on the outside and inside, but I will think that maybe there's a component of the variability that sometimes this was probably another question that we had on with the sensor, how much we capture the variability within an orchard and orchards that are taller and have, we tend to evaluate in these models the fruit that is more exposed because we target those that are we want to protect and we might not be targeting those that are below the canopy and then maybe that can play a role in the variability of the data that we collect as a ground
Yeah,
truth.
so I just want to say this. I know we are probably out of time. The models are good to get general understanding when stress is coming and so forth. And because I'm Prishna guy, I say get the direct measurement to do the actuation. So hence use sensors to actuate things. So yeah.
Yes,
Garrett.
we are on time, but let's give Garrett a chance to chime in and then we'll wrap up. Go ahead, Garrett.
I think it's been good discussions and really good presentations. For me, just wanted to make a couple comments on the overhead cooling. I've done a lot of fruit surface temperature readings, and I really like, and some of our growers use 10 minutes on, 20 minutes off. And the coldest part is actually that 10 to 15 minutes off because of the evaporation on a fruit surface temperature. So that's been working well. And a lot of that's based on Larry Schrader's work that he did with sunburn browning a long time ago. So 10 minutes on, 20 minutes off. And then the other thing that it was probably about 5 years ago, started seeing a lot more Phytophthora issues in apple blocks due to overhead cooling. And when I looked back at the weather data, the number of, at least for Washington, the number of days over 90 degrees didn't really change that whole much. But when I broke it down to hourly using the AgWeatherNet data, the hours of over 90 degrees in that overhead cooling window was greatly increased. And so I think that's one thing to keep in mind with the researchers is you have your big trends, but then also when we're talking about certain diseases like Phytophthora, it's how much water did you put on? And especially in some of those years, there was a lot of frost control that was done in the spring, and then in the summer, a lot of overhead cooling where it's just a lot more hours than what historically has been done in the past. That's all the comments I had.
Thank you, Garrett. Yeah, Garrett is
Yeah.
always awesome. He's our advisor, I guess, for AgWeatherNet anyway. So yeah, thank you, Garrett.
Thanks, Garrett. Okay, well, we are past the end of our time, so I'll hand it over to you again, Kristy, to wrap up.
Thanks, Sonia. I'll just share this screen here. And so first and foremost, I do want to again thank you to Emily, Kirti, Jeff, and Lav for your presentations today. That was really great. And I think it's a nice way to kind of get the conversation going for the coming weeks as well. So we're going to keep this moving. So next Thursday, we're going to have another same, what is it? Same bat time, same bat channel. June 18th, we'll be talking mitigation strategies, timing, and trade-offs. And then the following Thursday, we're going to keep going, talking about managing fruit after heat exposure. So we do encourage you to join those. You can register if you haven't already, you can register using the same link. So with that, we really do thank everybody for joining. Hope that it was valuable for you. And we are going to have, if it hasn't gone already, but Sonia, can you pop that link in the chat? We do always appreciate any and all feedback because, again, we are trying to continually improve these meetups. We feel that they're worthwhile. We hope that you do as well. So all feedback is welcome. You may also get it popping up once you leave this. So we appreciate that. So I think that's all. So on behalf of the organizing committee, thank you for joining us today, and we hope to see you back next Thursday. Take care, everybody.